Okay, let's talk about it. I mean, every single day, we are just bombarded with these incredible stories about what AI can do, right? You've got ChatGPT, Gemini, Claude, and they're all doing things that honestly feel like they're straight out of science fiction.
And look, it's not just hype. These things are really passing medical board exams. They're writing complex code from scratch and even composing some seriously beautiful music. The progress is just staggering. And it's so easy to see all that and think, wow, we are just a stone's throw away from real human level intelligence.
But what if that's not the whole picture? What if the very thing that makes these models so powerful, that transformer architecture, also has some deep, fundamental flaws baked right in, weaknesses that you can't just fix by throwing more data or more computer power at them? Well, that's exactly what we're going to dig into.
All right, so first up, we need to look past the headlines, cut through the noise. We have to separate the idea of just getting bigger from the idea of actually getting smarter.
And you know what's really interesting here? This isn't just some random critique from the outside. The data is actually coming from the big AI labs themselves, places like OpenAI and Anthropic. Their own research shows that, yeah, making the models bigger helps up to a point. But then you start to get diminishing returns. The gains level off. And more importantly, those fundamental gaps in real reasoning, in just basic common sense, they don't seem to go away, no matter how much data you cram in. So this gets us to the absolute heart of the problem. We've really got to unpack the core difference between how we as humans think and how these AI models think. It's all about the massive gap between genuine understanding and just being a really, really good mimic.
Here's the best way to think about it. When you or I learn something, we build a mental model of how the world works. We get that turning a key causes the car to start. Transformers, they don't do that at all. They just build a giant probability map. They know that the word start is statistically very likely to come after the phrase turn the key in the. But they have zero concept of an engine or ignition or physics. They are masters of correlation, but they have no clue about causation.
The linguist Emily Bender came up with this absolutely perfect metaphor for it. She called them statistical parrots. Think about it. They can repeat words and string together sentences that sound incredibly smart and fluent, but they don't actually understand the meaning behind them any more than a parrot understands Shakespeare if you teach it to recite it. So, if these models are just sophisticated parrots, what does that actually mean for us? Well, it leads us straight into one of the biggest, thorniest problems in AI today, the black box problem. Here's the deal. When a large language model gives you, say, a medical diagnosis, we often have absolutely no idea why it made that decision. Not even the people who built it can fully trace its logic. And you know those cool attention maps that supposedly show what the AI is focusing on? Yeah, turns out they can be pretty misleading. This is a huge roadblock if we want to trust these things in high-stakes fields like medicine or law. The galaxy analogy is just perfect. The system is so complex, you can't possibly track every single star to figure out why the whole thing is moving the way it is. Now, to be clear, researchers are working like crazy to solve this. There's this whole emerging science called mechanistic interpretability, which is all about trying to crack open that black box. They're literally trying to reverse engineer these digital brains, neuron by neuron, to see how they tick. But wow, it is an incredibly difficult, slow process. Okay, so let's put aside the philosophical limits for a second. There is another, much harder limit that AI is slamming into, the simple laws of physics and economics. Because the path we're on right now, just build bigger and bigger models, is completely unsustainable. This right here is the mathematical Achilles heel of the transformer. It's something called quadratic scaling. The core part of the transformer, the self-attention mechanism, it has to compare every single word to every other single word in the text. So what does that mean in the real world? It means if you just double the length of the text you're processing, you don't double the computing cost, you quadruple it, and that cost just explodes exponentially from there. And that insane computational cost has a very real, very big environmental cost. Get ready for this. According to Stanford research, training just one large AI model can pump out as much carbon dioxide as 5 cars over their entire lifetime. I'm talking manufacturing, fuel, the whole shebang. That is a massive sustainability crisis just waiting to happen. Okay, so we've covered a lot of ground here. The lack of real understanding, the black box, the insane scaling costs. It might sound a little bleak. So the big question is, what's next? What does the world look like after the age of transformers? Well, the good news is, researchers are already on it. We're seeing some really exciting new ideas pop up. First, you've got things called state space models, like Mamba, that are designed to be way more efficient and break that quadratic scaling problem we just talked about. Then there's this really cool idea called narrow symbolic AI, which tries to mix the pattern matching genius of neural networks with the clear, logical rules of old school AI. And some folks are looking straight to biology, trying to build models with things like working memory, so the AI can actually hold on to information and, reason. So at the end of the day, what's the big takeaway from all this? I think it's that we have to see transformers for what they are. An absolutely revolutionary, world-changing chapter in the story of AI. No doubt about it. But they are just that, a chapter. They're not the end of the book. They're a stepping stone, not the final destination. Which leaves us with this final, massive question. As we keep pushing forward, we have to keep asking ourselves, are we actually getting closer to building true intelligence, real understanding? Or are we just getting better and better at engineering an incredibly sophisticated, incredibly convincing illusion? The answer is going to define the next decade of AI.